Hello students, welcome to the course Verilog HDL. In the previous video, we discussed two problems, exercises. One is about designing an your own my not, my and my OR gates using only NAND gates. And from that, you have designed a second exercise that is about my XOR gate. Okay, and also you have understood how to apply the stimulus for 4 inputs, and you have seen the access at the output. Okay, so in today's video we'll see a combination of 3 inputs, that means 8 possible combination of inputs you will have. So it is a full adder design, and that too using only basic gates. Okay, so not your own gates now, so you can use Verilog primitives. Okay, and we'll do the stimulus module and we'll see it. Okay, output. So just note down the question. The 1-bit full adder described in the chapter can be expressed in a sum of products form. Okay, so this is another expression I have. So there what I have used, A XOR B XOR C in. Okay, so now I am using the this expression. So they have given the expression already, so no need to write the logic symbol or truth table. Okay, but anyhow truth table is required to assess the output. Okay, so truth table is necessary, final verification of output. But since they have given already the expression, okay, so even if you write the truth table and then you write the k map, even you are getting the same. So we have seen this one, okay, in the last when I'm discussing 1-bit adder. So we have seen this k map. Okay, and how the entries are coming. So like 1 1 1 1, so all single ones were coming. And when you write this, okay, so when you write the individual expression for this, so we are going to get this. Okay, A B C in, A bar B C in bar, A bar B bar C in, A B bar C in bar. So you can just verify. Okay, so you have A this side and you have B and C in this side. Okay, so you are going to get the same result. Okay, not much. So this is not further simplified, kept as it is. Similarly, C out also we are written this one. So C out, when you write the truth table, so you'll get the 3 combinations we have seen, right? So it is A dot B, B dot C in, and A dot C. So you can refer the previous video where we have discussed 1-bit full adder. So how you get this? Okay. So now for this design, we will write a gate diagram. And what is they have told? Assuming A, B, C in are the inputs and sum and C out are the outputs. The name of that also they have given with the design. Design a logic circuit to implement the 1-bit full adder using only and, not, and OR gates. So in the chapter which we have discussed, there we had the XOR combination, right? So we had and OR, and OR, and XOR combination you had, right? Half adder using that we have done. Now it is using basic gates only how to do. That is the difference. Okay. So write the Verilog description for the circuit. You may use up to 4 input Verilog primitive. Okay, so 4 input gate you can use. Okay, and OR gates. Write the stimulus for the full adder and check the functionality for all input combinations. So 3 inputs means 0 0 0 to 1 1 1. All the 8 combinations you have to verify the output. Okay, so about the logic symbol and truth table I have discussed in the 1-bit full adder. So you can go back and see in the 4-bit full adder video. Okay, so now I will draw the logic diagram for these two waveform, these two Boolean expressions. Okay, so what you have, A B C in first case, then you have A dash B C in dash. Okay, then you have A dash B dash C in. Okay, so you can note down, and A B dash C in. Clear? Fine. So just we'll try to write that. Okay, so that is the first step. But in the, so in books and all, they will not give this. Okay, so solution directly they will give Verilog program. Okay, so we'll try to do the design. So first case, what you have, A B C. Okay, so whichever way you can do. Okay, so you write the 3 input A B C. That means it is a product, right? So you want a 3 input AND gate. So you have 3 input AND gate, and for that you have to give some variable. Okay, I call it as S1. Okay, that means someone. Okay, so some part, no, that's why that I will keep. So this is seen, okay, not just seen in our design. Okay, accordingly you write. Then you have A bar B seen bar. That means every time you should have here the complement of that gate. Okay, so A bar. Okay, so better than that we can use the vertical things. Okay, so just we will use that vertical. So hope you know how to do vertical. So this one. Okay, so just we'll have, so that it is easy for both to write. So this is the A. So then we will have the NOT gate connected to this. Okay, so hope you understand. So this is the A bar line. So then I will take the second input. Okay, B. So it is also, I will connect the NOT gate. So one of the time we have. Okay. So since I'm writing from mouse may not be clear, so you write neatly. Okay, so then I have third input C in. Okay. And for that also NOT gate is connected. So this is better than previous one. Okay, so now you have to name this first 3 NOT gates you have used. So output of that. Okay, so I call it as A underscore N. Okay, for better understanding. So this is B underscore N in terms of programming language. So this is, you will consider already seen is there. For that underscore N will add it. So the now if you got these 6 lines, now it is easy to construct any of that. Okay, so first we'll do the sum part. So where you have to do ABC. Okay, A, then B, and then C. So all no complement. So all 3. So you connect the AND gate, and this is the first output. I call it as S1. Okay, it is ABC in. Next you have A bar. So A bar means complement line you have to use. So you draw the A bar. It should be neat here. Then you have B. Just see your question. Okay. B, and then you have C in bar. So C in bar is here. So connect the second AND gate. So you'll get second output S2. Okay, clear? So then third one, what combination you have? A bar, B bar, C in. Okay, so that means again you have A bar. So now you have B bar here, and then so both A bar, B bar, then C in. So C in is as it is, so don't confuse. So connect the third gate, AND gate, 3 input AND gate, and name the output as S3. Okay. So then fourth one, what you have? A, B bar, C in bar. Hope it is clear. B bar and C in bar. Okay, so see if I have made any mistakes, so just you correct it. Okay, because we could not do any interaction here. Okay, I hope I have done correctly. Okay, so I got the 4 products now. So in the question also they have told you can use maximum 4 input primitive gate. So I have 4 outputs now. These are the inputs to the OR gate now. So what we will do? So we will connect it to an OR gate now. So try to make it neat. Now we'll draw a OR gate, and OR gate output is now the actual sum of the full ladder. Okay, so this is what the design. So previously we have used the XOR gate for producing the sum. So XOR and XOR, XOR A, XOR B, XOR C. 2 XORs we have used and we got the sum. Now it is not so. You have 3 NOT gates and 4 3 input AND gates and 1 4 input OR gate. 3 input AND gates and 1 4 input OR gate. Okay, so just you can write so that it is easy for you to write in instance. Okay, all are and these are NOT gates. Okay, okay, better you mention and. Okay, So it should be easy when you write the Verilog description. So now in this you got the sum. Similarly, you can do the Cout also, that is the carry. So it is a product of two. So first one is A dot B. So just take the two input A and B. Now require two input AND gate. Clear? And you got the first product A dot B. I call it as C1 signal carry 1. Okay. Then B dot Cin. Okay. So I have to connect B and Cin. So connect the second AND gate. So name it as second carry product. Okay. C2. Then finally you have A Cin, right? Or Cin A. So you got the third product also. Okay, which is C3. So now you require a 3 input OR gate to add these 3 signals. Okay. So these things you have done in basic electronics, right? Even in the logic design, digital system design also you have done it. Okay. So but I am recalling it now. Okay. So hope it is clear. So this is the C underscore out. That is what in our question. Okay. So this is about the sum and this is about the Cout. For Cout you require only 2 input AND gate and 3 input OR gate. Okay. So this is an OR gate. Okay, and these are all AND gates. Okay. So better write so that easy to call it in the Verilog program. Okay. So hope this design is understood now. So having this knowledge, so now you can write the Verilog description. Okay. So how you write now Verilog description? So just tell me. So first you have to write the module name you give, and then list of ports. So inputs are A, B, C in, and output is some Cout. So this is the picture. Okay. Logic symbol picture. Inside that it may be constructed in many ways. Okay. Previously we have seen one way. So now this is another way. Okay. So this is the full ladder logic symbol. Okay. So like a black box. Okay. So A, B, C in, some Cout. So A, B, C in are inputs, some and Cout are the outputs. Then what are the intermediate wires we have used? A N, B N, C in underscore N, right? So these three we have used output of NOT gate. Then we have some outputs, individual product we have S1, S2, S3, S4. This should be declared as wire. Then C1, C2, C3 you have. This should be declared as wire. That is the declaration of variables. That is also over. So then just you have to call the gates. So first you call NOT gate. Output is A bar and A. Next second NOT gate, B bar and B. Next third NOT gate, Cin bar underscore N is the output, Cin is the input. Next you have to call the AND gates. So S1 is the output. Then correspondingly you have to write there A, B and Cin. Okay. So whatever you are using the names, same thing you should use in the program. Similarly you have to write S1, S2, S3, S4. Similarly C1, C2, C3. And then finally you have to write the sum. So output is sum and here inputs are S1, S2, S3, S4. And here Cout, C1, C2, C3 are the inputs. Okay. So that's what I'm going to show you quickly. So that, so from this only you have to write. Okay. So if you are writing, practicing, just pause the video here, write it, let it be wrong. Okay. So then write the program. Okay. So then correct it where you have made the mistake. So this is the only way you learn the programming. Okay. Otherwise it is going to be a by hearting concept. So this design you just translate into Verilog hardware description now, and then so it will boost your confidence. Okay. So pause the video and write down. Okay. I will continue. Okay. So after that you can continue the video so that you can verify the thing. Okay. So this is the program what I mentioned there. Okay. So module name I have given FA, full adder. ABC in, some Cout are the list of ports, and then output some Cout, input sum. So this is the first part, right? Second part, all the declarations you have used, all the declarations, NOT gate, AND gate. Okay. All S1, S2, S3, S4, A bar and B bar and C in bar and then C1, C2, C3. Okay. So even the comments shown which products they are. Okay. So it is shown here. Then you have to call the NOT gates, 3 NOT gates as I mentioned. Okay. So this is the NOT gate section. So then these first four are the 3 input AND gates. 3 input AND gate. So immediately you can write the OR gate also, but they are following the hierarchy. Okay, so first level you had a NOT gate, right, in the design. Second level you had all the AND gates in the design. So third level you had the 2 OR gates, like that they have written. And these 3 are 2 input AND gates. Okay, that is belongs to carry. So these are 2 input AND gates. And finally you have OR gate. So this is a 4 input OR and producing the sum. See here, sum S1, S2, S3, S4. So accordingly I has written ABC in. Okay, so just you can verify whatever signals we have used in the design. Okay, so if already you have written, you can verify. Okay, and where you have made mistake, so what is the mistake happened, just go through. Okay, so then see out. So this is the 3 input OR gate. So all the design constraints are followed. So once you have done the design, you have to go back and see the question. So all the things have followed or not. Okay, so far, so you have written the Verilog description. So what is left out now? You have to write the stimulus module now and then check the output. So stimulus is very easy, as you have written previously for your own gates, XOR and OR. So now just you have to increase one more input ABC in, and your combinations will increase 0 0 0 to 1 1 1, and remaining all part is same. Okay, so how you write the program, clear? So hope this design is understood. So no much time I am spending in programming, right? Much I have to spend in design part, gate level. So if you know that, this will be clearly understood to you. Okay, so I will go further. You can pause and you can just verify. Okay, okay, so this is the stimulus module. So module name I have given test now. Even you can give stimulus, no issues. Input should be given as register and then output should be given as wire. Okay, so this is what we have done previously also. So then your design is called here. So full adder was the name and its F1 instance name is given F1. So pass the input in same manner, ABC in sum cout. So this is a connecting ports by ordered list. Okay, so second thing also done. And then we have written the any, I told you last, right, any order you can write. Okay, so monitor is written and then we have given the input. So initial, begin, and then 8 combinations are written over here. See, so this block initial, begin, and so here initial is 0 0 0. Okay, so it is 0 0 and 0, 1 bit 0, then 0 0 1 0 1 0 0 1 1 1 0 0 1 1 1 1 0 0 1 1. Okay, so all the 8 combinations are done. Okay, next initial, begin, monitor statement you have to write. Simulation time, because 10 time delay seconds have given, so it will start 0 10 20 30 40 50 60 70 till 70 it will run. Okay, so then whatever values will change, it will be reflected here, ABC in, then cout and sum will be calculated. Okay, so to verify this you require the truth table now. Okay, so you can verify the previous design 1 bit full adder, so truth table is there, or you can just do the truth table and verify. Okay, so this is about the finally end module. So this is about the full adder stimulus block. So now just we will verify for this. Okay, so how output is coming. Okay, okay, so this is the output. So initially 0, the inputs are 0 0 0, so sum and cout are 0 from the truth table, right? Next, at a simulation time 10, so Cin is changed to 1 now, so cout is 0, though carry, sum will be 1. Okay, this is the truth table, you can verify. Then 20 time, so you got the next combination 0 1 0, so now cout is not there, so sum is 1. Okay, then 30, so it is 0 1 1 combination now, so sum will be 0 and there is a carry produced here 1. Okay, next another 10 time minutes, so 40 it will come, so now 1 0 0 combination will come, so now again, so sum is 1, only 1 is there now, so no carry generated, so it means 0. Next 15 simulation time, 1 0 1 combination will come, again sum will 0 and carry is produced here. Next 1 1 0, 2 ones are there, that's why again sum is 0, carry is 1. And finally you have the 1 1 1 combination, so for that sum is also 1, cout is also 1. Okay, so this is the design. Okay, so hope it is clear. So the design, it is following the same procedure. Okay, So logic symbol, truth table, Boolean expression, gate level diagram, then Verilog description, then stimulus module, and finally the simulation output. Okay, so this is a 7-step procedure. So already they have given the Boolean expression. So your 3-step procedure is reduced. Okay, symbol, truth table, and logic expression part is removed. So remaining 4 you have to do. That's what we have done. So first we have done the design gate level diagram. From that you have written the Verilog description, and then you have written the test bench. Okay, simulation stimulus module, and finally we have verified the output. Okay, hope it is clear. So with this we have completed the 3 exercises. Another 2 exercises are there that we'll see in next video. So again we'll see the gate delays part. In this 3 we have taken assumed gate delay is 0. So we'll take one of the exercise also, how to assign gate delay with minimum, maximum, and typical values, and one RS latch program. Okay, RS latch and multiplexer is there. So that we'll see in the next video. Okay, thank you.